This is Lab 4, Oscillations for Physics 1. The purpose of this lab is to observe and measure the motion of a mass swinging in an arc while the spring is oscillating and measure the energy change in the system. This lab uses Newton's second law, Hooke's law, and the energy principle to predict motion. This also takes into account the change in kinetic energy, the change in gravitational energy, the change in the spring's potential energy, and the change in total energy. We will construct a program to model the motion and then compare the computational model to the experimental model. So the procedure for this lab is to use a tracker to analyze the motion of the swinging object, as we see here. And as we can see, we're getting results on this right side. So we can save these results to CSV and then use that CSV to create a computational model to predict the motion. I will be using Python through GlowScript and compare the observations through spreadsheets. I will be using Excel. So our results show actually that the predicted motion and observed motion are similar in both the X and Y axes. We definitely see more similarity in the Y axis motion. So here is the Excel diagram. This is observed motion up here. I did some comparisons between the X position and Y position, and the standard error for the differences in the Y positions, which is down here, about 0.04, is significantly lower than for the X positions, which is 0.08. So this is comparing how different the X and Y values are for the computational model and the observed. And we can see also here in the graphs as well that the motion in the Y direction is much more similar. So this is the observed graph. And then down here, the Y motion appears to be much more similar. So these are our initial conditions. The observation, the initial position is from the observed position and tracker at time 0. And then we also work with initial velocity, which is as shown. This is from time 0. And the time of our last observation is at 9.972. Or initial position is as shown, initial velocity is 0 at the start. And then the time of the last observation is 9.972 seconds. Okay. These are our key concepts, beginning with Newton's second law. We have that the net force of an object is equal to the change in momentum over the change in time. That's a very fundamental physics concept. The velocity update formula that relates velocity and the net force. And then we have that the velocity update formula is also related to the position update formula, as we've discussed in previous labs. So the next important concepts and formulas we use for this lab are the energy principle that states that the change in the energy of a system is equal to the work done on the system by the surroundings plus the exchange of thermal energy between the system and the surroundings. Then we also use the formula for translational kinetic energy, the spring potential energy, the gravitational potential energy, and then a formula for finding the length of the spring. So here's our formula for period of oscillation. We can actually visually see the period of oscillation here. So we can kind of compare these, the differences between the 2 points in an oscillation. And we've actually done that calculation here. It amounts to 1.519 seconds. We can then use that to find the spring constant K by plugging in our mass of 0.402 kilograms and our T. Then we can also solve for the relaxed spring length by using the length of the spring under compression and subtracting our M, our mass times the gravity constant, and dividing it by our calculated K constant to get the relaxed spring length. So you can see this number over here. It's about 6.9. And then here is our formula for the relaxed spring as well. And then we can see all of this in our code. We have formula for the length. Here are our constants over here. We have the formula for the length, the system energies, and then we have our gravitational force, force of the spring, net force, fundamental physics concept, updating the object's velocity with momentum principle, updating the spring, calculating the energy changes, and these are applying the same formulas we went over. So is the energy principle satisfied? It is satisfied because the total energy, which is the orange line in our computational model, is equal to 0. So the estimations of the oscillation periods with calculations shown below can be found by averaging the periods of oscillations for the X position and the Y position. So the differences in these numbers may deviate from factors such as drag forces, camera distortion, and other possible sources of error I will discuss at the end. So the system is Earth, accounting for gravity, the spring force, the mass of the object, and then the surroundings are really none in this case. The sources of errors do come from not accounting for drag or loss of energy. And then we also have possible sources of error from disparities in Tracker's auto-defining features. This can also come from the fact that Tracker has been updated recently. The time frame used for the computational model delta t may not be show as accurate of a result as if it was like a smaller delta t. And then again, the computational model does not account for drag force or loss of energy.